Hello everyone, just give me a moment to check whether the streaming is working or not. Just give me a moment, please. Yes, it is working. And if you have any questions, any doubts, hi Shriya, Sorba, hi, hello. So if you have any questions, any doubts, please feel free to ask me in the comment section below. Right? My internet is slightly lagging on this device. Yeah. Okay, thank you. So today this is the last part of moving charges and magnetism theory. Next class we will discuss the previous year questions from this chapter, and then we will start with the next chapter. Okay, now moving charges and magnetism. So far what we have discussed and what we are going to discuss in today's session, let's look into that at a glance. So we have discussed Lorentz force. So the force that acts on a charged particle when just give me a moment, my mic is just disturbing me a little bit. Yeah, I guess this is fine. Now Lorentz force is what? Lorentz force is the force which acts on a charged particle, right? Just let me check once audio. It's working. So Lorentz force is the force which is acting on a charged particle, right? So whenever the charged particle moves in a electric and magnetic field combined, it experiences Lorentz force. Next is motion of a charge in magnetic field. So when only magnetic field is present, that Lorentz, the magnetic component of Lorentz force makes the charge move in a circular path, right? We have calculated the radius of the circular path. We also have calculated the frequency and time period, etc., right? Next is magnetic force on a current carrying conductor. Now starting from the charges, now we have moved on to a current carrying conductor. Whenever there is a current carrying conductor, it experiences a force, and that force we called it BIL sin theta. Bill sin theta, that was the force that was acting on a charged particle. Now magnetic field, because a current carrying conductor is experiencing a magnetic force, it should also produce its own magnetic field as well, and that magnetic field we have calculated due to a current carrying element, Biot-Savart's law, and then we have applied it to find magnetic field due to a straight wire as well as a current carrying loop. We will see that again in today's session as well. Okay, so these two, Biot-Savart's law, magnetic field due to a straight conductor, and circular current loop. These are the applications of Biot-Savart's law. From there, we have moved on to Ampere's law. Okay, Ampere's law is another version of the Biot-Savart's law. So in the exam, there was once a question which was asked that which of the following is equivalent to Biot-Savart's law. The answer would be Ampere's circuital law or Ampere's law. Okay, so for that we have applied it to find for a straight current carrying conductor, we have calculated the magnetic field again using Ampere's law. We have also seen the magnetic field due to a solenoid. We have seen the force between two parallel current carrying wires. That was our last topic in last lecture. Magnetic field versus electric field comparison, and mu naught and epsilon naught, that we are going to do in today's session in a while. Okay, now torque on a rectangular current loop. So this is the topic that we will start off today. Current carrying loop as a magnetic dipole, and galvanometer, ammeter, voltmeter. These are the four things that we will discuss in today's session. So let's start with the torque acting on a current carrying loop. But even before that, let us go and discuss another important topic, which is magnetic field due to a current carrying loop. Circular current loop as a magnetic dipole. This one is first. Obviously, we have done this derivation. We are not going to do the derivation today. Just want to revisit once more. So there is a, just a second. There is a current carrying loop. Okay, it is located like this. Obviously not, this is not the loop, it's a circular loop. So we are observing it from a angle, that's why it is looking like this. Okay, it's like a 3D thing of a and projected on a 2D screen, right? Hello Shriya, hello Nama Nade, Namma Nade, Rankina Kade. I don't mean the I know first option, first meaning, but the second part of the thing I don't know. Yes, good evening. It does not matter, Shriya, how many of you are watching right now, because many students they watch it later on. Okay, so even if you are watching live, the basically the advantage of watching live is when you watch live, you can ask questions. So if you think that I am super good, I don't ask any questions, I will just watch the videos later on. Then you can watch it later on, right? The same thing with recorded sessions as well. So if you are attending a live session, basically your main idea is that you have to ask question, you need to learn interactively, okay, so that I also know that okay you have learned, right? So that is the major point of live session. If it is a recorded session, you have no option to ask any questions. Whatever I will teach you, you have to listen to me, and if you have any doubts, you will leave the leave for after the lecture with those doubts in your mind, right? So that is the only difference between a recorded session and a live session. So live session you can interact with me, right? I can read your chat, I can reply to your comments, right? So here we have a current carrying loop, okay, and we are trying to find magnetic field at a distance x from the center of the loop. The radius of the loop is given by capital R. We did that derivation, right? We took a small portion delta dl over here. Due to the dl, we applied Biot-Savart's law, calculated the magnetic field, and then we realized that magnetic field exists only along the x-axis. So magnetic field only along the x-axis, there is no magnetic field along the y-axis, and based on that we did this derivation, right? This derivation we have done in our last class. Okay, if you forget this derivation and if you want to know how to do this derivation easily and quickly, you can go and check my last class, there I have done this derivation. Okay, today we are going to take a few special cases of this derivation, namely one special case. First of all, at the center of the coil, if you want to find at the center, you just put x equals to 0. This point comes over here, you get the magnetic field at the center of the loop. But today's case is very special. We are trying to find magnetic field at a distance which is very, very far away from the center, or in other words, the coil is very small, the distance is relatively large. So in that case, what happens if the distance is relatively bigger than this r? Okay, for example, say x equals to 100, r is equal to 1. Okay, so if you are doing that in this, if you put that value in this equation, okay, you can see that the value of x square is far greater than the value of r square, right? Even if it is 100 and it is 1, in that sense, even it is 10, it is 1 also. X is 10, r is 1. In that case also, x square is 100, r square is 1, right? So that does not change much. So in that case, what we can do, we can ignore this r square, whatever is added in the division part, whatever is added. So small numbers can be approximated whenever this is an in addition form. You cannot ignore this r square. This r square is in the multiplication form. So remember that. Okay, whenever you are doing approximation, you only can approximate when it is addition or subtraction. Multiplication and division approximation does not work like that. Okay, so because r square is very, very small compared to x square, so we will ignore r square completely, and this can be written as mu naught I r square divided by 2x cube. Now sir, why this complicated number becomes so simple, x cube? Let me explain that as well. So x square plus r square to the power 3 by 2. Now because this condition is satisfied, we will ignore this term completely. Ignore means we will remove it completely, we will put 0 in that number, okay, and we will say, okay, so we are left with x square to the power 3 by 2, or x square into 3 by 2. So 2 cancels and we get x cube. So this complicated number, whatever complicated looking number, that number becomes x cube only. Now next, what is our task? We have to multiply pi in the top and bottom portion. We need to multiply pi at the top and bottom portion. Okay, then this quantity pi r square. What is this pi r square? This is r. So pi r square is the area. Pi r square is the area of the loop. So pi r square is the area of the loop. Okay, so this becomes our area of starting point. Okay, now this area we will write it as a. Okay, in many cases area is important, so we will generalize this pi r square to be a, and slowly we will move it. We will say that this quantity I into a is a quantity which is called magnetic dipole moment. I into a is called magnetic dipole. Why so? I will explain, don't worry. I into a is magnetic dipole moment. Okay, and in some cases we will add if the number of turns is equals to, for here number of turns equals to 1, that is one single loop. But if we have a coil generally have multiple number of turns. A coil generally have multiple number of turns. In that case, the same term becomes NIA. Okay, if for n number of turns, the this quantity becomes NIA, and we denote it with the symbol small m. It is called magnetic dipole moment, right? So this is NIA, National Investigative Agency. Remember this. This is going to be super duper important in today's all the derivations, all the calculations that we are going to do. So this is the National Investigative Agency, NIA. Now let's go back to our calculation. So let's put this m over here. Here we are considering only one loop. In many cases, as I mentioned, there will be multiple loops. We will consider NIA. NIA is general, IA is specific for n equals to 1. So let's put that value here. So m divided by 2 pi x cube. Now let us do one more thing. Let us multiply 2 in the top and bottom. Let us multiply 2 in the top and bottom. Then we get the magnetic field expression as mu naught by 4 pi 2m by x cube. Now why this is important? So magnetic field we got is mu naught by 4 pi 2m upon x cube. Now I am saying this is super duper important. Why it is important? If you recall, the magnetic field due to an electric dipole, okay, magnetic field due to a electric dipole on its axis. So this is plus q, this is minus q. Okay, on its axis, the electric field on the axis of a dipole was given by 1 by 4 pi epsilon naught 2p by r cube. Okay, the distance from the center was given by r, right, the point where we are trying to find the magnetic field, right, and the equation was E is equal to 1 by 4 pi epsilon naught 2p by r cube. Is there any similarity? So here the constant is magnetic constant mu naught by 4 pi. Here it is a electric constant 1 by 4 pi epsilon naught, right? Here it is 2m by x cube. Here it is 2p by r cube. Okay, so that means here x is the distance, here r is the distance. So that means these two quantities must be similar. So it was called electric dipole moment. It is called magnetic dipole moment. So that is why we call this term as magnetic dipole moment, just to compare it. Now what is a dipole? If you remember, dipole has a positive charge and a negative charge. What about magnetic dipole? Magnetic dipole nothing but like a magnet which has a north pole and a south pole. So magnetic dipole means it has a north pole and a south pole, right? That's what we call a magnetic dipole. Okay, so magnetic dipole. Now what does mean of a current carrying loop? So when you are considering a current carrying loop, it behaves like a magnet. Basically, that is the major point of discussion of today, that current carrying loop, when it is carrying a current, it behaves like a magnet. Now, magnet has two poles. So how do we identify which is what? So suppose we have two loops. One is carrying current in the anti-clockwise direction. Another one is carrying current in the clockwise direction. And if you are wondering, if you watch this loop from this side, it will be clockwise. If you go behind and watch the same loop, it will be anti-clockwise. Okay, same loop from this side clockwise, from behind the loop it will be anti-clockwise. Okay, you can actually see that. You can draw a circle on a paper. You see that this is clockwise, and rotate it, it will be anti-clockwise, right? So that is one interesting fact. Anyway, now if you are drawing this, okay, you need to draw S and N. Okay, if the current is flowing along the sides of the S, then it is a south pole. Okay, if the current is flowing like this, then this will be the south pole. And for north, we have to be little creative. We have to be little creative. If the current is flowing like this along the open ends of N, then it will be north pole. So anti-clockwise current gives north pole, clockwise current gives you south pole. Now that is something you need to remember, but if you remember using the pictures, then it is much easier to remember. Okay, you don't need to think out clockwise or anti-clockwise. I confused. You don't need to be confused. If you just remember the pictures N and S, that's it. That is sufficient for you to identify this is the north pole, this is the south pole, right? Clear? Now let's move on and go back to our original discussion. Okay, so torque on a rectangular current loop. So now we have, instead of circle, we have a rectangular shaped loop, current carrying loop. Okay, so this will also experiences a magnetic force on its arms. Okay, and if you recall that, if you have a current carrying conductor placed in a magnetic field, okay, it will experiences a force given by BIL sin theta. And if the angle is 90 degrees, that sin theta becomes 1. So that is the normal case. Okay, now assuming that they are not normal, okay, we have another current carrying loop. It is carrying a current in the opposite direction in the presence of some magnetic field. Some magnetic field is present there. So this is carrying current, say I, this is also carrying current I. Okay, the internal force between them, we are not considering it right now. We are only considering force acting on this due to external magnetic field. External magnetic field is very strong. So what will happen to this wire? This wire will experience as a force BIL sin theta. Suppose this direction is in this direction, then the other wire will experience as a force in the exact opposite direction. Okay, the other wire will experience as a force in exact opposite direction. You have to put theta to be minus theta. Okay, if this is plus theta, then that will be minus theta. Sine of minus theta is minus. So the direction of the force will be opposite. In fact, I have drawn the arrow like this. It is actually out of the paper, and it will be into the paper. Okay, so the force acting on this wire is out of the paper. Here the force acting on the paper is into the page of the paper. Now if you have another two wires like this, which is connecting the wires, these two wires are on the same direction as the magnetic field. The force acting on this will not be there. Okay, force acting on these two wires will not be there. So even if there is a force, the force will be exactly opposite direction and exactly opposite direction. So it will cancel each other. There will be no relationship between these two forces. But here these two forces are not only opposite, they are also on a different plane. Here these two forces are on the same plane, so they will cancel each other. But these two forces will not cancel each other. You need to find the torque due to these two forces. The force, any one of the force, is given by magnitude of the force given by BIL sin theta. Magnitude of the force, Bill sine theta. Now we are trying to find the torque. How to find torque? First PUC concept. So when there are two forces acting on an object at two different directions, then you take magnitude of any one of the forces. If this is plus, this is minus, by the definition it will be there. But anyway, so if this is plus, this will be minus. Okay, and so what happens to these two forces? The distance between them is, say, x. Then the torque is given by force into distance between the two forces. This is called moment of force or torque. It is called moment of force or torque. Okay, so something that you have learned in your first PUC. So that concept we have applied in the electrostatics chapter as well. Here also we will apply. Suppose the length of this wire is L. That L is coming over here. This is a breadth of the rectangle. So suppose this breadth is given by B. This breadth is given by B. Now what is the torque then? The torque will be force into this distance. The torque will be force into this distance. So let's put that value over here. You will get BIL sine theta into B, or BIL into B sine theta. Right? This is a rectangle. This is length. This is breadth. So length into breadth is what? Length into breadth is the surface area of the rectangle. So this will be basically BIA sine theta. So the torque acting on the loop is BIA sine theta. Now this is on one single loop. Now instead of that, if you have n number of loop, that is one loop, the loop is not completed in one go. We have multiple loops. You have a rectangular shape, and you have winded multiple loops on that rectangle. Then that total torque, the total torque becomes B N I A sine theta. This is for n equals to 1. This is for n equals to n. Okay, so this is the normal formula, BNIA sine theta. Okay, you can remember the maximum torque. The torque which is maximum is given by the maximum value of the torque is given by when sine theta equals to 1. If sine theta equals to 1, that is theta is 90 degrees. So when the current carrying loop and the magnetic field are perpendicular to each other, in that case torque becomes maximum, and that is given by BNIA. Okay, if you want to remember this formula, you have to rearrange it and you have to write BINA. Bina. Okay, Bina, the musical instrument that classical musicians play. Okay, 4 strings. The same thing here, Bina. Bina is basically the torque, maximum value of torque acting on a current carrying loop in an external magnetic field. So this is the maximum current torque acting on a current carrying loop, right? So now let's go back and look into the equation. So torque is given by I into A into B. Now this derivation is a good 3-marker question been asked in your midterms and pre-boards from time to time. So you need to practice it. Easy derivation, as you can see, nothing is there. You need to consider a current carrying coil, then force acting on one is BIL sine theta, the other one will be minus BIL sine theta, and these two forces will not be there. Okay, generally we consider magnetic field is already perpendicular parallel, that to explain it properly, that these two forces, there are no forces because of these two wires. Okay, because for these two wires theta is either 0 or 180, so in that case BIL sine theta becomes 0. So there are no forces acting due to these wires. Okay, and because the plane is parallel to this direction, okay, this will experiences a torque, and that is Bill sine theta, and from there you can derive this, okay, Bina sine theta. Now Bina sine theta, in the previous part I have shown you that this quantity NIA, okay, NIA is called magnetic moment. This is called magnetic moment of the coil. In the last one it was a circular loop, here it is a rectangular loop, but loop is a loop. So for circular loop if it is NIA, for a rectangular loop also it will be NIA. So this is the magnetic moment of the loop, okay. So we can replace the torque as B m sine theta. This is the general form, right? Bm sine theta. Okay. Now torque is a vector quantity, magnetic moment is a vector quantity, B is also a vector quantity. So when you are writing this in the vector form, it will be torque equals to m cross B. Remember the order is m cross B. This is the expression for torque acting on a magnetic field or acting on a current carrying loop. Okay, so this is the expression for torque acting on a current carrying loop. So this derivation is important, and you don't need to draw this kind of diagram. Simple square loop with a magnetic field pointing at it is sufficient. Okay, now before going into any further, just wanted to show you that how can you join our free YouTube course absolutely free of cost without paying anything. So what you need to do, you need to just go into the description section of this video, or you can click on the in the live chat there is a link shared with you. You can go there and you can click on that link, register yourself. Once you register yourself, you can come to our YouTube channel as well. Okay, you can come to the YouTube channel. Here if you come over here, this is the live video that is going on right now. You come down in the description section, you will see here join free ACE KCET 2027 course. Once you click on this link, you will see that basically this is a 0 rupee course. Okay, you don't need to pay anything for this course, so don't worry. So 0 rupee course, you click on buy now, and then you need to register for the first time. Okay, next time onwards you don't need to register, you just need to log in using your mobile number and OTP. So once you log in, you will get access to this, and we currently have some tests live as well. Okay, live and upcoming some mathematics test is there. Okay, you can get some live tests. You will get all the lectures that we are doing. You will get the PDFs of all the lectures that we are doing in our classes as well, and it will be absolutely distraction free. You will not be distracted by some ad views or something happening on the right hand side. It is completely distraction free, and exactly the way there will be support of Ved AI as well. You can ask questions to Ved AI. Okay, Ved AI will be there to help you out. Okay, and the class notes will also be added in this session. You can see the class notes as well. Okay, the notes will be shared over here. All the lectures that we are doing in our session, one shot be it live sessions, all the PDFs will be shared to this link only, right? So that is one important point for all of you. You should join this right now by clicking on the link, and then come back and let's continue with our discussion. In between I will have some drink to water. Okay, now let's move on with the question. A circular current loop of magnetic moment M is in an arbitrary orientation in an external uniform magnetic field. The work done to rotate the loop by 30 degrees about an axis perpendicular to its plane is. So this is an interesting question. Circular current carrying loop. No information is given. If you see that question is not has not given you any information about current passing through it, magnetic field there. So basically, what is the first of all logical answer to this question should be something which is very common. Okay, that is one. So magnetic moment M is given and magnetic field is I think external magnetic field is not mentioned, but it should be assuming that this is given by B. The work done to rotate the loop 30° about an axis perpendicular to its plane. So this is the axis of the perpendicular axis to the plane. Okay, so this is the perpendicular axis to the plane. Just a second. Mm, hmm. Okay, this is the perpendicular axis to the plane. Now, if you rotate this loop, so this is the current carrying loop. Just a second. Okay, this is the current carrying loop. Okay, the work done to rotate the loop by 30° about an axis perpendicular to this loop. Okay, so magnetic moment, arbitrary orientation in an external electric field. Now, if you rotate this loop, basically it's area vector of the loop and the magnetic field vector, whatever direction it can be, the angle of this orientation does not change. So this A and B, even if you rotate it, area vector A will still point at this direction. Area vector will not change. If you rotate it, in other direction, if you rotate it like say along this axis, if you are using this axis, then the angle area vector changes. So you have to do some work. But in this direction, the area vector, even if you rotate it, suppose this is a CD or a old gramophone record, if you have seen that, okay, it is rotating along this, right? So there is no work you need to do because the angle area vector of the angle of the area of the loop does not change. Area vector remains same, B vector is fixed, so the angle between A and B remains same. So if angle between A and B remains same, the work done will be 0. Work done will be 0, right? So that is one very interesting question, and it was asked in KCET few years back. Year is not mentioned, but it was from KCET, I think 2022 or 2021. Okay, now a moving coil galvanometer. So we have learned that if you keep a current carrying rectangular coil in a external magnetic field, then it basically experiences a torque. Now that principle we can apply in a rectangular, we can apply to a um, device which can measure how much current is flowing, because torque, we know that what is torque. Torque acting on a current carrying loop is given by B. Now maximum torque, assuming the torque is maximum, the maximum torque is given by B now. Okay, now if we can make an arrangement where torque is always maximum, okay, and if we can figure out that how much torque is acting on this, we can actually calculate this current. We can actually calculate this current. So this is a device which can measure the current flowing in a circuit. Okay, if you can take that device and fix it in a circuit, it will tell you that okay, this much current is flowing in the circuit. So that device is called a galvanometer. So galvanometer is based on the principle of torque acting on a current carrying rectangular coil. So the question that will come in your PU exam is that what is the principle of moving coil galvanometer, and derive the expression for current. So these are the two things. Easy derivation. Derivation is not difficult, but you know to remember that the principle behind working of a galvanometer is that when a rectangular current carrying, or not rectangular, when a current carrying loop is placed in external magnetic field, it experiences a torque. That is the basic principle of galvanometer. Now here the current does not flow always, only when it is connected to the circuit, As soon as you connect to the circuit, there is a current that flows through this coil. This is the this four dotted line, four lines that you can see is the current carrying loop. So it is basically the current carrying loop. And if there is a torque, what happens when you apply a torque? If you remember in rotational motion, when you apply torque on an object, suppose you apply torque on an object, it starts rotating around the axis. If you give it a point, okay, it will start rotating around the axis, and it will keep on rotating as long as the torque is acting. It will keep on rotating, right? So galvanometer, if you do not control it, what happens? The needle, suppose that you have designed a galvanometer using the principle, okay, the needle will keep on rotating like this, but it does not happen. Galvanometer has a range. It can only rotate within certain range. It cannot rotate like infinitely, right? So how does that happen? So basically inside a galvanometer we have fixed a spring. If you see, there is a SP written over here. SP is not superintendent of police, it is spring. Okay, that spring is a spiral spring which is like this, right? This is the spring that we have fixed inside the galvanometer. Now what is the role of this spring? So when the galvanometer, when the coil is trying to rotate, the spring is trying to hold it back. The role of this spring is, it is trying to hold back the coil. Okay, so basically it is producing a counter torque. It is producing a counter torque in the exact opposite direction and exact same value. So the counter torque is also bina, but it is in the opposite direction. For a spring, we know that force, if the force constant is given by K, okay, spring constant or force constant of a spring, okay, if the spring constant is given by this constant K, then force is given by K into X, and the torque is given by K into theta. Theta is the angle of rotation. Suppose normally when there was no torque, okay, the angle was here. This is the normal position when torque is 0. So here torque is 0. Here some torque is acting. Then this angle is actually your theta. So and the theta has to be in radians. These things are important. So theta has to be in radians. Then the torque which is balanced by the spring is directly proportional to the angle theta, and if the spring constant is known K, then this torque is given by K theta. Okay, so as we are only considering the maximum torque, we will say this is K theta. Now if you compare these equations, equation 1 and equation 2, you can get K theta equals to bina. Okay, our target is to find this current I. So I equals to K theta by B N A. K theta equals into B N A, or we can write K divided by B N A into theta. K divided by B N A into theta. So this is the current that is flowing in this galvanometer, right? And from here we can say that the current passing through the galvanometer is directly proportional to the angle. So if you can somehow scale that, so zero current means obviously 0, okay, and if we can scale that, it is directly proportional to the theta. Higher the angle theta, more current it is passing through it. Okay, if we have a proper scaling mechanism, if we can scale that, we can measure the current. That is flowing in the circuit. Okay, so that is one thing. But galvanometer as only a galvanometer, it is not super good as a device to measure current. Now few things that we need to discuss about after this, that is the constant K divided by BNA. This is a galvanometer constant, it is denoted by symbol G. For a given galvanometer, this is a constant. Okay, you will do an experiment where you actually will find this constant value. Okay, so this is called a galvanometer constant. You will find this in your experiment. Okay, in your college when you are doing the experiments in for second PUC exam. Okay, there will be a figure of merit of the galvanometer. Basically, this quantity, close to this quantity, you will find. Okay, now this is galvanometer constant. Okay, so the galvanometer constant, because why it is constant? Because spring which is fixed inside the galvanometer is fixed. You are not changing it. You are not breaking the galvanometer and taking out the spring. I want to fix a new spring. No, right? So spring is a constant for a given galvanometer because it's a fixed, sealed from outside. Magnetic field is basically dependent on the magnets which are fixed inside the galvanometer. Again, that is also fixed. You have fixed some, the designer, whoever manufactured the galvanometer, they have done some fixed structure inside it. So this magnetic field is also constant. Number of turns. So number of turns are present inside the galvanometer coil. Again, that number of turns are also constant. Area is again the area of the coil that is fixed inside the galvanometer. That is also constant. You are not doing anything inside the galvanometer. All these components located inside the galvanometer. That's why this is called galvanometer constant. Okay. Now another important quantity that we call is sensitivity. There are two types of sensitivity. One is current sensitivity. Another one is voltage sensitivity. Okay. Current sensitivity is what? How much current you can measure per unit difference. Okay. So if you are measuring the angle theta, okay, and then divide by the current I, then that is called current sensitivity. Okay. Current sensitivity is basically, if you see that, theta divided by I, theta divided by I, so that is actually BNA by K. This is the current sensitivity. Voltage sensitivity, theta divided by V. So how sensitive the galvanometer is to current, how sensitive the galvanometer is to voltage. So if there is a small fluctuation in the current, how much deflection it will give, that is called current sensitivity. And if there is a small change in voltage, how much deflection the galvanometer will give, that is voltage sensitivity. It is given by, what is voltage, by the way? Voltage is I into R, Ohm's law. R is the resistance of the galvanometer. Okay, then it will be BNA divided by K into R. This is the voltage sensitivity. This is current sensitivity. This is voltage sensitivity. Okay. Now from the outset, from the equations itself, it might appear that current sensitivity is directly proportional to area and voltage sensitivity is also proportional to area, right? Obviously B for a given galvanometer, assuming constant, N is number of turns, okay, K, if you keep K also constant, if you increase the area of the galvanometer, okay, if you increase the area, then both voltage and current both are proportional. What about the number of turns? If you come to the number of turns, then also it seems that both of them are directly proportional. But here is a catch. One of them depends on N, another one does not. Okay, which one depends on N, which one does not? So directly SI or current sensitivity depends directly on N. So if you increase the number of turns, current sensitivity increases. If you triple the current number of turns, current sensitivity gets tripled. Okay, current sensitivity is directly proportional to number of turns. Okay, so if you suppose you have increased the number of turns in a galvanometer, initially say by increasing current by 1 ampere, so this was 0, this is 1, angle that you are getting say 10 degrees, okay, or 10 whatever 10 value. Okay, if you increase the number of turns to 3 times, for same change you will now get a 3 time angle, that is the current sensitivity. Okay, the deflection is more for same change, the deflection will be more if the galvanometer is very sensitive. We want, actually in practical cases, we do not want it to be too sensitive, we do not want to be very less sensitive, we want to be a balanced sensitive. Okay, if this it is too much sensitive, what happens, even small fluctuation the needle will keep on fluctuating, you will not be able to take a reading. If it is very stiff, even the if you increase the current by say 5 ampere, the needle is still not moving. That also we do not want. We want it to move, current sensitivity should not be too small, it should not be too high as well, it should be somewhat balanced. So 0.1 change, it will move. 0.01 change, perhaps it will not move. That's what we want. For voltage sensitivity, however, there is a R in the division. What is R? R is the resistance of the coil. Okay, resistance of the coil. So what is the resistance of the coil? Coil is basically this, right? So number of turns, basically if you increase the number of turns, what happening here? The length of the wire increases. More number of turns basically means more number of length of the wire. If you rewind it and take the length will increase. So increasing the length, basically increasing the resistance as well. So resistance, in other words, we can say is directly proportional to number of turns. Okay, so N by R is actually a constant term. Okay, N by R is a constant term. If you increase the number of turns, resistance of the wire also increases equally, proportionally, because resistance is directly proportional to length. Okay, that means N by R is a constant. So that means voltage sensitivity is independent of number of turns. Voltage sensitivity cannot be increased by increasing number of turns. Current sensitivity can be increased, voltage sensitivity cannot be increased. There was a question where it was said that the number of turns in a coil was tripled, in a galvanometer is tripled. Okay, what happens to voltage and current sensitivity? Current sensitivity tripled, voltage sensitivity tripled, current sensitivity remains same, voltage sensitivity tripled, current sensitivity tripled, voltage sensitivity remains same. Okay, none of these or one of the other answer was given. So you need to remember, voltage sensitivity cannot be changed by changing the number of turns. That's why I put so much focus on this apparently simple concept, right? So these are the main concept of this galvanometer. Now let's look into the question. The torque acting on a magnetic dipole placed in an uniform magnetic field is 0 when the angle between the dipole axis and the magnetic field is. So torque acting on a magnetic dipole is mb sine theta. That is the general expression. Okay, m cross b or mb sine theta. So if torque is 0, okay, if m and b are not 0, then only other option is sine theta equals to 0. Sine theta equals to 0. When sine theta is 0, when theta is equals to 0. Okay, so the angle between the dipole axis and the magnetic dipole moment is 0. Okay, easy question, easy answer. Now, galvanometer, even though we use it to measure current, it is not a super good measuring device. Okay, it can only tell you if there is a current passing on a circuit or not. Why? Because it is not regulated. It's an unregulated device. It is basically designed on the principle of torque acting on a coil. Okay, but we have not optimized it for our day-to-day life. Okay, it's like you have designed a fan which has the raw power, but it is not optimized for our 220 volt AC current. Okay, so it will not give you proper speed. This is kind of a prototype. You can say galvanometer is like a prototype, which is the initial developing stage. Okay, it is a good device to detect if there is a current flowing in a circuit or not, but it is not a good device to give you exact value of current in many cases, because when you are designing a proper circuit, you don't want that your circuit is influenced by the galvanometer. For example, I'm giving you one example. We have a circuit, suppose a resistance, a battery, some current is flowing in the circuit. I want to measure this current. For that, what I did, I put a galvanometer in series, which is the principle, right? In series, current remains same. In series, current remains same. So I put a galvanometer in the in series. So now whatever current is flowing in this circuit, that current will be measured properly by the galvanometer. But will this current be same as this current? Will this new current, whatever is flowing in this circuit after connecting the galvanometer, will that value be same as if there was no galvanometer? Because you are doing in a controlled environment. Everything is same. R resistance same, voltage V same. Okay, but you have added a galvanometer. Galvanometer itself has its own resistance. So what will happen? This will add up the resistance back to this. It will add up the resistance back to the circuit. So overall current in the circuit will reduce. Suppose here the current was what? According to Ohm's law, it is V by R. Now here what will be the current? The current will be V by R plus Rg. Obviously these two are different quantities, so current will actually reduce. You don't want that, because you tested in your laboratory saying that this circuit will work perfectly if you fix it in your home. The person took the device, he fixed it in his home, and it immediately burned and got destroyed. Then he came back running after you, they saying that what circuit have you designed? It is not working, it is completely burned. So you have to see to that when you are doing it in your laboratory using a galvanometer or whatever device you are using, that device gives you this current, not something which is being influenced by the galvanometer itself. You want closer value to this current, not something which is less than this current, right? In your laboratory you find the current to be 10 ampere, which is fine. You give it back with removing your galvanometer, you give back the circuit. He fixed it in the home. Now the current becomes 20 ampere and circuit got burned. So that's why it is important that whatever device that you connect to measure current has to have a very low resistance. So all current measuring device must have a low resistance. That is super important. So galvanometer as it is own, it can measure current, but that current is not accurate that we want to measure. We want to measure this current without affecting the resistance of the circuit by much. That is not possible by the galvanometer. Galvanometer, as soon as galvanometer as its own, it's coming into the circuit, it is influencing the circuit itself and reducing the current, which is not our desired result. So ammeter being a current measuring device, an ideal ammeter means most ideal that we want, should have zero resistance. So ideal ammeter should have a zero resistance, so that it does not influence the current that is flowing in the circuit. Okay, in practical ammeters, the resistance is kept as low as possible. In practical ammeters, the resistance is kept as low as possible. Okay, to convert a galvanometer into an ammeter, we need to connect a shunt. What is a shunt? Shunt is a small value resistance. Shunt is a small value resistance in parallel to the galvanometer. Okay, so that is what we want to achieve. So suppose we have a galvanometer and this is the resistance of the galvanometer. I want it to measure current. To measure current, what we need to do? We need to connect a shunt resistance in parallel with the galvanometer. Okay, now that does two things. It does two things. First of all, it reduces the current that is flowing in the galvanometer. So galvanometer is designed for, say, very small amount of current. Okay, so that problem is solved. First of all, galvanometer cannot measure ampere or high value current. It can only measure up to certain milliamperes. Small currents it can measure. So that one problem is done. So we want a device which is basically having a low resistance. Now if you connect a small value resistance in parallel, we know that there is a property of resistances in parallel. Hello Arjun. Hello Arjun Shetty. Hello. Yes, you are new to the class. If you have any questions, any queries during the class, feel free to ask me. I will try to answer as much as possible. Right? Now, so galvanometer is basically a device which have a very small current allowance. It can allow very small amount of current through it. Otherwise, it will basically burn the circuit. We don't want it to be burning the circuit. That is one point. we only want that the current, whatever current that is coming, okay, we are measuring it successfully, but without burning the galvanometer. So how can we do that? The only way to do that is by uh, having a secure path for the current. So here we have the original galvanometer. It has a resistance. We denote it like this. Okay, sometimes we denote it with capital G, sometimes we denote it RG. Okay, in your textbook it was denoted with RG. Okay, there is no harm in it. Only thing confusion is that resistance of the galvanometer and galvanometer constants people forget and mix up. These two are not same thing. So just for avoiding confusion, I am using RG today. Okay, so now what we have done, we have connected a shunt in parallel. We have connected a shunt in parallel. What is the meaning? What does this do? So if the galvanometer resistance say 10 ohm and I have connected a value 1 ohm, the overall value of this combination will be less than 1 ohm. Right? In parallel combination, the equivalent resistance becomes lower than the lowest value. So this equivalent capacitance becomes smaller than 1 ohm. Right? This one will become smaller than 1 ohm. That means we want a device which actually gives you lower resistance. That's why it is called a shunt. Shunt is a path through which extra resistance can be siphoned off. Now suppose a current which was coming towards the circuit is given by say I. Okay, a current which we want to measure in the circuit, the same current, this current, okay, this current that we are trying to measure is given by I. Now that current is coming. The galvanometer itself is saying, I do not want this high amount of current to pass through me. I will allow only a certain amount of current which I know this is my limit. I will not go beyond this limit. I will only take Ig amount of current. Remaining I will let it go. So for example, you visited a marriage ceremony and they are giving you some sweets. Okay, they are giving a lot of sweets. You only know that I can only eat 2 sweets. I will not be able to eat more than that. You are rejecting, no, I don't give me more than 2. Okay, so this is the limit of the galvanometer. Galvanometer know its limit. It's only saying I will only allow Ig amount of current. Remaining current I will allow it to pass through my brother which I brought along with me. I will all pass on all the sweets to my brother. Okay, so this shunt brother, he will take all the remaining I minus Ig and it will pass through this. Okay, shunt resistance generally denoted by symbol S. Shunt resistance is denoted by symbol S. So the Ig current passes through the galvanometer. Galvanometer is happy. Remaining I minus Ig passes through the shunt. Shunt is very happy. Now we have to do a little bit of mathematics. What mathematics? In parallel combination, we know that the voltage across both galvanometer and the shunt should be same. Right? In parallel combination, if you remember, parallel combination of resistances, the voltage drop across the parallel combination remains constant. Same thing happens here as well. The in the parallel combination, the voltage across galvanometer and voltage across shunt remains same. Now what is voltage? So then we have to go back to Ohm's law. Ohm's law says that voltage is given by V is equal to IR. So here the current is for galvanometer, the current is Ig, the resistance is IRG. This is the IR for galvanometer, right? And for the shunt, it is I minus Ig into S. Okay, so this is the voltage drop across the shunt. Now these two has to be same. The voltage drop across the galvanometer and the shunt, because they are connected in parallel, has to be same. So these two has to be same. Now what we are trying to find here? We are trying to find this unknown current I. Galvanometer current, maximum value of the galvanometer current is known to us. We designed the galvanometer, so we know that maximum maybe say 0.1 microammeter or 0.1 milliammeter can pass through the galvanometer. So we know that value. So Ig is known. This I current is not known. So we have to figure out the value of I using this equation. So you need to simplify that. Ig, Rg equals to is in minus ig into s. Minus ig into s comes over this side. We write is equals to ig common rg plus s, or I equals to rg, sorry, rg plus s divided by s into ig. Okay, this equation must be written if you are answering the question how to convert a galvanometer into voltmeter. Sorry, how to convert a galvanometer into ammeter. So along with this statement that ideal ammeter should have a zero resistance, we achieve that by adding a small value resistance in parallel. You also have to show what is the expression for the current that is passing in the circuit. So if the current in the circuit here is given by I, okay, the current through the galvanometer is Ig, through this is I minus Ig, then also you need to show that current I over here is given by Rg plus S by S into Ig. Now, is S value is fixed for a given, is S value is fixed? No, S value is not fixed. It depends on how much maximum current you want to measure. Okay. So, if you want to measure a very high value current, you have to keep the RS very, very low. If you are measuring a small value current, you can keep RS relatively high. So, the value of the current that you are trying to measure, based on that, you have to adjust the value of RS and tune your ammeter. Now, there was a question that RS for a ammeter and RS, not RS, say S, shunt resistance for ammeter and shunt resistance for a milliammeter, who has higher value, who has higher resistance. Remember that higher the amount of current that you want to measure, shunt value should be proportionately lower. Okay, proportionately lower. Higher the current you are measuring, more current should pass through the shunt. That means the shunt should be very, very small. Okay, whereas for higher value of current, we do not want to add too much load on the galvanometer, but still, if the current itself is small, galvanometer will say I can handle this much current, no problem. So in that case, the shunt resistance value can be higher. So it it is a very what should I say, very tricky question, where students will think that, okay, if the current rating is smaller, that means we need a smaller shunt resistance. Actually not, it is exactly opposite. Okay, so if the current you want to measure is smaller, the shunt you require will be higher, relatively higher. Okay, because Ig value is fixed. That is one point. Ig and Rg values are fixed. Okay, only thing you need to do, change the shunt value and correspondingly you change the scale and measure current. Interesting, isn't it? Next is what how can we measure the voltage? How can we measure the voltage in a circuit? So again, let us go back to the discussion that we are having. Just give me a moment. So we want to design something which measures voltage. So how do we measure voltage? We have a resistance. We have a resistance. Suppose we have a battery. Some current is flowing here. Okay, battery has voltage V, resistance is R. Now this is the, in this case, according to Ohm's law, we know that the voltage across this is same as this voltage, right? That is the Ohm's law. Now some current is passing in the circuit. So what is this voltage? V. V is equal to I into R. Okay, V is equal to I into R. Now what? Now we want to measure this voltage in our quest to measure the voltage. How do we measure voltage? We need to connect a measuring device across this resistance, assuming that we are just simply using a galvanometer to measure the voltage. Okay, if you use the galvanometer, measure the voltage. Now what happens? Suppose this resistance value is very high. Okay, this galvanometer resistance is not very high, not very low. It is somewhere in between. So what happens is that the overall resistance of this combination decreases. Overall resistance of this combination is decreases, because parallel combination, whenever you combine two resistors in parallel, the overall resistance becomes lower, right? So in that case, what happens is that the current that was flowing in the circuit gets lower. Okay, because the current gets lower, okay, the voltage drop across the resistance becomes lower, and you get a wrong reading again. Okay, because in parallel combination, galvanometer resistance is neither too high nor too low. Based on the resistance that you are using, okay, your reading will be completely different than what you should get. Your currents will be different, your voltages should be different, right? So you don't want that. You want that I want the exact current and exact voltage. I don't want to change the circuit parameters. So in that case, what you have to do, you have to have a galvanometer with a very high resistance. You want to have a very high resistance, so that the overall resistance of the circuit does not get affected. So if you know that two resistances, when you connect two resistors in parallel, say R1 and R2 are parallel, okay, the if the difference between their resistances is very high, the equivalent resistance is very close to the smaller value. Okay, suppose this is say 1 ohm, this is say 100 ohm. Okay, then the equivalent resistance between these two will be very close to 1 ohm. Okay, so that's why if you can keep the galvanometer resistance very high, our overall circuit resistance does not change, and we get most accurate result. Okay, that is one very important point. So an ideal voltmeter, this is slightly wrong, ideal voltmeter should have infinite resistance. Ideal voltmeter should have infinite resistance. If the resistance is infinite, then whatever parallel connection you do, the resistance will not change at all. Okay, ideal ammeter should have zero resistance. Ideal voltmeter should have infinite resistance. Okay, good evening, good evening. We aren't getting any videos for chemistry from Diksha Karnataka channel, so we can follow the last year chemistry videos for Diksha Karnataka channel PU2 board exam 2027. Rama DN for UB. Yes, you can follow previous year chemistry videos. We had Aishwarya ma'am, we had um, uh, another teacher, actually two three teachers were there in last year. Okay, actually both all of them have left our channel, unfortunately, and we are still looking for a chemistry teacher, which will be we will get them very soon. We are trying to we actually have finalized one of the teachers. We are trying to get them as soon as possible. Okay, that but due to some issues, it is not yet possible to bring them here. Okay, but as soon as it is done, we will put a little bit more focus on chemistry. But don't worry, last year videos are very good. Yes, we will do year appropriate videos for this year as well. Just give us a little more time. Okay, give us little more time. We are trying to figure it out. Like you are worried, we are also worried, but don't worry. Yes, last year's, for example, midterm, if you are watching a midterm video for your midterm exam, we have done almost all the chapters are covered in the last year's video. Questions almost same. Yes, year specific, there are 10 to 15% questions can be different, because some questions did appear in last year's board paper. Those questions generally do not come or repeated, but we do not only focus on those questions, right? We say we are doing 100 questions, out of that say 10 20 questions came in last year, so remaining 80 questions you can still use, right? Remaining 80 questions you can still use this year as well. Okay, otherwise it is most relevant. Yes, some year wise updation for KCET, for example, KCET last according to the last year's trend, how you need to modify your preparation strategy, etc., that you need to see a little bit in detail, right, Rama? So yes, for your PUC and KCET, you can still watch those videos. They are still one of our they were one of our best teachers in our channel, right? Saini ma'am as well as Aishwarya ma'am, and then we had I forgot her last name, but she was also there. So we had three teachers last year. They were teaching chemistry. We are trying to bring one more faculty very soon. But as long as it is not happening, you can watch our previous year videos. No issues. Okay, I think you will find the playlist section there. Right, Rama? Right now, to convert a galvanometer into a voltmeter, we need to connect a high value resistance in series in the galvanometer. But as I mentioned, ideal galvanometer should have a very high resistance. Okay, ideal galvanometer should have a very high resistance. Now we cannot my mistake. Ideal galvanometer should have an infinite resistance, but infinite resistance practically is not possible. So practically, infinite resistance means you have to cut the galvanometer. Then it will no current will pass through it. You will not be able to measure anything. So what we can do, we can keep the resistance of the galvanometer very high. And how can we do that? This is the easiest part. We just need to connect something in series. If we connect a very high value resistance in series, then the galvanometer resistance becomes very high, and as we know, voltage sensitivity is given by NAB by RQ. Already given you this formula. Same formula is mentioned over here as well, right? And remember that voltage sensitivity is independent of number of turns. It depends on area, it depends on B. Okay, it is dependent on K as well, but it is independent of number of turns. Okay, now let's move on and see what is that voltage that we are measuring. Okay, what is that voltage that we are measuring? So V equals to so here we had a galvanometer, its internal resistance Rg and a external resistance, high value resistance R. Okay, now here the galvanometer is saying that okay, no matter what, I will not allow just a second. I will not allow anything other than my capacity. My capacity is Ig. I know if I allow any current more than Ig, I will get burned. So the galvanometer will only say, okay, I can eat two biscuit. I will eat only two biscuit. Maybe I will share some with my friend. Okay, but I will not take anything more than two biscuits. So that is only the input current that can pass through it. So Ig is the only input current that can pass through it. So Ig is current that is entering. So what is the voltage that you are measuring? Voltage that you are measuring is the current that is passing into the total resistance. So this is a very simple, easy formula. Galvanometer to voltmeter is one of the easiest concept. You just need to connect something in series, and you also have to show the voltage that you are measuring. The measured voltage is given by V is equal to Ig into Rg plus R. This is a concept from where we have seen a lot of short numericals in PUC as well as KCET. Short numericals based on this single formula. Now there are few concepts that you need to remember, that whenever we say the full scale deflection of a galvanometer, full scale, you will hear that full scale deflection, FSD. So what does that mean? So whenever this Ig is the limit maximum current that is passing through the galvanometer. Okay, so even if you have designed an ammeter or a voltmeter, remember full scale deflection refers that when the current in the galvanometer is maximum. Obviously, I have a capacity of eating two biscuits. That does not mean that I always have to eat two biscuits. I can eat one biscuit also, right? I can eat half biscuit also. So basically that means this is the maximum value of current that can pass through the galvanometer. In practical cases, suppose I am using a 5 milliammeter galvanometer. 5 milliammeter galvanometer means it can measure anything starting from 0 to 5 milliammeter. When you are measuring this much current, that is called full scale deflection. This is a very interesting term. Many students do not know. Okay, this is called full scale deflection. Full scale deflection means starting from zero, the needle move to the maximum possible position. That is full scale deflection. Anything between say 0 0.5, 1, 2, 3, 4, 5. So all these in between values also it can measure, right? But full scale deflection refers to the maximum possible current, and that refers to this current Ig. Okay, that refers to this current Ig. If you want to reduce this Ig, that is also possible by adding series and parallel. But remember that whenever we talk about full scale deflection, the current refers here is the maximum current. Okay, we will see some numerical questions. I think in our upcoming sessions we will see PYQ session. Okay, now magnetic field versus electric field. So there is a small comparison. So far we have seen some similarities and some dissimilarities between magnetic field and electric field. So let us find out what is the difference between them. So both are long range, both electric and hi Shardamma. Hello Ammu. How are you? You need to wait, right? When I am teaching, I cannot reply to your comment. I need to finish a topic, then I can check the chat, right? Hi Shriya. I think Shriya is watching from the beginning, right? Yes. Now, magnetic field versus electric field. So both are long range, since both depend inversely on the square of the distance from the source of the point of interest. Okay, so if you just consider magnetic field and electric field due to a dipole, okay, both uh, 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 are dependent on the square of the distance from the source. So electric field is proportional to 1 by r square. Magnetic field is proportional to also 1 by r square. Both are dependent on 1 by r square. The principle of superposition applies on both cases. Okay, so if you are trying to find magnetic field at a point, the same way you do add them vectorially, same way you do for electric field as well. Okay, so electric field and magnetic field, both cases you can apply superposition principle. What is superposition principle? When two different magnetic field acts on a same point, or two different electric field act on a same point, how do we find their magnitude? How do we find the net force, net electric field? So we just need to add them using vector algebra. Vector algebra means triangle law or parallelogram law. Using that you can find their magnitude, their addition. So that is superposition principle. Superposition principle is basically adding them together. Vector addition or scalar addition. Here, because B and E both are vector quantities, we will need to use vector addition. In some other cases, in some other quantities, we use scalar addition as well. Okay, the electrostatic field is produced by a scalar source, namely a electric charge. Okay, the magnetic field is produced by a vector source, namely I into dl. So that is the major difference. Who is the thing that produces electric field? Electric field is given by kq upon r square. So here electric field is produced by a point charge. Charge is a scalar quantity. Now Biot-Savart's law tells us the magnetic field is given by mu naught by 4 pi, okay, I dl sine theta divided by r square. So here this I dl is actually a vector quantity. Okay, dl is a length is a vector quantity, and when you multiply with I, it is called current element, and this is a vector quantity, and this is the source of magnetic field. So scalar quantity producing a vector quantity, here vector quantity is producing another vector quantity. Okay, so that is the major difference between electric field and magnetic field. Electric field is produced by scalar, magnetic field is produced by a vector. So that is a super duper important point to remember. The electrostatic field is along the displacement vector joining the source and the field point. The magnetic field is perpendicular to the plane containing the displacement vector, uh, and the current element is ideal, right? So electrostatic field along the displacement vector joining the source and the field point. So if you say this is the current charge q, this is the point where you want to find the magnetic electric field, you join them, either it will be away from or towards based on the sign of the charge. This is the displacement vector. Nothing new. Displacement vector is nothing super duper complicated over here. Displacement vector means you join the 2 points, extend it, that's it. Okay. But magnetic field, actually, if you take ideal, suppose this is the direction of ideal, okay, and if you are trying to find magnetic field over here, it is not just simply you join them, it is perpendicular to both ideal, okay, as well as this point P. It is either, so this is, in this case, it will be out of the paper. So it is not only perpendicular to ideal, it is also perpendicular to this. So common perpendicular is this direction. Okay, so remember that. In case of magnetic field, it is perpendicular to both current element as well as displacement vector. There is an angle dependence in Biot-Savart's law, which is not present in the electrostatic case. The magnetic field at any point in the direction of dl, the dashed line is 0. Along this line, q is equal to 0, sin q is equal to 0, and dv is equal to 0. Okay, so there, if you take up directions, for example, this direction or this direction, so along the line, whatever line that you are considering, current carrying conductor, okay, along that line, the magnetic field is 0. But for charge, there is no such point where electric field is 0. Electric field, you can go all the direction. For a single point charge, you can find the electric field everywhere. Okay, now let us look into a small derivation. Okay, this derivation we will use in our another chapter, electromagnetic waves, as well, but just for us, very simple calculation. Okay, I will show you. Let's not spoil the fun. So what we are trying to do, we are trying to find the value of mu naught into epsilon naught. This is the thing that we are trying to find out. Now we know that mu naught by 4 pi has a fixed value. So we divide it by 4 pi, we multiply it by 4 pi. Now we also know that if we can write it as 1 by 4 pi epsilon naught, this also has a fixed value, right? So it was there in the multiplication, so we have to bring it as a division of division. That's why we are writing it like this. Okay, so that means mu naught by 4 pi is what? It's basically 10 to the power of minus 7. 1 by 4 pi epsilon naught is what? 9 into 10 to the power of 9. Right? Now, let's take this value as division as well. We get 1 by 9 into 10 to the power of 16. Okay. Now, let's invert it. We get 1 by mu naught epsilon naught equals to 9 into 10 to the power of 16. Now, why this value is super important? Basically, what we have done, we have taken reciprocal on left hand side as well as right hand side. So here it was mu naught epsilon naught, so it becomes 1 by mu naught epsilon naught. Here it was 1 by 9 into 10 to the power 16, it becomes 9 into 10 to the power 16. Okay, and that is equals to 3 into 10 to the power of 8 whole square. 3 into 10 to the power of 8 whole square. So what is this value? This is a very special value. This is the speed of light in vacuum. So this gives you c square. So from here we can write speed of light in vacuum is actually given by 1 by square root of mu naught epsilon naught. This is the speed of light in vacuum. So this is a very special derivation. So the mu naught and epsilon naught are not random quantities. They are linked with each other because they basically the speed of light, which is a universal constant, is linked with this quantity, right? So this is the end of session. One question I have: a galvanometer of resistance 50 ohm is connected to a battery of 3 volt along with a resistance of 2950 in series. A full scale deflection of 30 deviations is obtained in the galvanometer. Okay, so voltage is given, galvanometer resistance is given, the external resistance is also given, and it is saying this is the full scale deflection. So if you remember, what is full scale deflection? Full scale deflection is basically the maximum current that can pass through the galvanometer, which is Ig, right? So we can calculate Ig. Next step is given that in order to reduce this deflection to 20 divisions, the resistance in the series should be. So basically we want to reduce the value of the current that is passing in the circuit. 30 divisions, Ig is fixed. So what is that Ig? Ig here for the first case, the voltage divided by the galvanometer resistance divided by the external resistance. The voltage is 3 volt, Rg is given by 2950, and the external resistance is 50. Galvanometer resistance is 50. Galvanometer resistance is 50 and the external resistance is 2950. Okay, that will be 3 by 3000. That is 10 to the power of minus 3 ampere. So this is the current, that is the maximum current that can be allowed through the galvanometer, and that gives us the 30 division deflection. I cannot change this value of current. What I can do, every time this much amount of current is passing in the circuit, the same amount of deflection will be there, right? So voltage is fixed, Rg is fixed. If we can change the value of R such that the current that is flowing in the circuit gets lower than this value of Ig, then it can be reduced. So how much current we need? The output current. The output current that we need must be 2/3 of this Ig. Why 2/3? Because originally it was 30. I want to reduce it to 20. So 0, 0 cancels and we got 2/3 Ig. Okay, so I want a current to reduce the division. We want to reduce the current, right? So how much current we want? We basically the ratio of the divisions. Okay, and into 10 to the power of minus 3. This much current I want. So this is our output current. Okay, so 2/3 10 to the power of minus 3, and that should be equals to the voltage that we have applied divided by the Rg and new resistance. This new resistance we have to find. So voltage is 3, okay, Rg is 50, and this is R. Okay, now do the cross multiplication. Do the cross multiplication. You get 50 plus R dash equals to 3 into 3 divided by 2 into 10 to the power of minus 3. That is 9 by 2 into 10 to the power of 3. That is 4500. So that means R dash will be 4500 minus 50. That is 4450. So the answer will be 4450. Right? Interesting question. Now I think there are two homework questions. Take a screenshot of this, or you can go in the link given in the description and join the KCET batch. From there you can get the PDF of this lecture and you can solve these questions. Mention the answer in the comment section below. Okay, or you can pause the video here and try to solve it. First, one question is slightly tricky, the second question is easy. Okay, try to solve them and answer them in the comment section below. I want to show you once more how can you join our free YouTube batch. Just click on the link in the description of this video. So once you come over here in our live session, okay, here you will see that this is the live session that I am teaching. Okay, you just click here, join free ACE KCET 2027 course. Now you click on this link, you will be redirected to our batch, which is free of cost. Absolutely, you don't need to pay anything for this. Once you come over here, you will get access to our batch. Okay, all physics, chemistry, physics, maths and biology as of now. Okay, whatever lectures that we are doing here in YouTube, that will be available along with the class notes, along with the tests, along with the quizzes. Everything will be available here only. Okay, so make sure you join here, as soon as possible. Do not delay it. Okay, more you delay, basically you are losing out on uh, all the content that is coming. Okay, you can even take some assignments. The assignments will be added. I think there is a mathematics assignment is going on. Okay, some mathematics test is going on, so live and upcoming. Some tests are already completed, so you can see maths, physics, one physics test, one biology test, math, two mathematics tests already completed. Okay, these are the live ongoing tests. You should try and attempt them as soon as possible. Which one? Which derivation? Shardamma. Shardamma, which derivation you want? This calculation? This one? Shardamma, if you are here, please respond which derivation you want. This one? This one? So this is basically starting with multiplying mu naught and epsilon naught. Okay, mu naught is mu naught by 4 pi, and so basically you are what you are doing, mu naught by 4 pi. So you are dividing with one extra 4 pi. So you need to add that in the top as well, right? Now what you are doing, mu naught by 4 pi into 1 by 1 by 4 pi epsilon naught, right? So I can write, say I have a number 3, I can write it as 1 by 1 by 3, right? Same meaning. So that's what we have done, and after that we have put the values and then taken a reciprocal on both sides, and from there we got the value is very close to the value of speed of light, and from there we actually calculate the speed of light, right? Shardamma, I hope that is clear. Tanim, this one is a PYQ. This question was a PYQ. I'm not sure about the other two questions. Okay, this is a PYQ, by the way. This one I am not sure. I need to check from where I have taken. This is a PYQ, by the way. Okay, right? Shardama, clear? Okay. Thank you, guys. If you want to get the PDF, please click on the link as I mentioned in the video. There you will get the PDF. Okay, very, very soon. Till then, bye. See you in the next live. There will be one more chapter coming in our one shot. Do watch that. And till then, bye.